All right, we're gonna go over this section 6.4, and in this section we're talking about an application using congruences, okay, or the language of congruences, to actually to the what's called the Gregorian Calendar. So the objectives of this section are, very short. Basically, we're going to find a formula, so to determine the day of the week for a given date after the year 1600 in the Gregorian calendar. Then we're going to present some examples of doing calculations giving certain dates and find what is the corresponding day of the week that date actually corresponds to. All right. First, there is an interesting history concerning, the calendars. So I'm just going to leave that for you. All right. There is a very short, actual history in the textbook, but there is much more extensive history if you are interested in this kind of topic. All right. In fact, the Gregorian calendar goes back to the second half of the 16th century. It's actually they started with in, all right, so this is the Gregorian calendar. Started in 1582. All right. Before that, they found there some, some trouble with previous the Julian called calendar. All right. So first to understand, the derivation in here, we need to distinguish between different types of years. So there are basically two types of years. The one which we call it the common years. And these consist of 365 days in each one of these years. And then we have what is called leap years. And this has 366 days. Now, leap years are characterized by, so a year is a leap year. A year Y is a leap year if Y is divisible by 4. Y is divisible, or it's a multiple of 4. But however, except for what is called for century years, and those are the years that end with 0, 0. So each one of these years is going to be divisible by 4. So we call these these are called century years, okay? And a century year is a leap year, okay? A century year is a leap year if it is divisible by 400. Well, so we're going to distinguish between these different types of years. Okay, so we have the common years, which is most of the years are common years. every 4 years we have a leap year, and then also we have what's called century years, all right, and some of these century years are leap years. Now, our objective is, remember, to determine the day for a certain date, all right, starting from the 1600. So if I want to count, just to give you an idea, what are, the leap years? For example, we have 1601, 1602, 1603. These are common years. All right, and of course 1604, this is a leap year. Now the century years, starting from actually the so the century years since this 1600, okay, century years after 1600 are 1700, 1800, 1900, and all of these are not leap years, because none of these numbers actually divides 400. However, the year 2000 is a leap year. All right, so this is the way we're going to actually proceed. We're going to go step by step to develop this formula. All right, once the formula is developed, of course, applying it is very, very simple. So the actual work on this section is to try to understand the derivation of the formula that we use to determine the day, of the week for a certain date. All right, so let me begin by this. First of all, I was convention to make the calculation easier. Since in a leap year, we add an extra day, basically, to February of the year, of that year. We're gonna think of our formula, okay? So we are going to begin to think, or actually to so we're going to do the calculations by assuming each year begin with March 1st. So March 1st, as far as the calculation that we're gonna do, all right, is gonna be the first month of the year, all right? This is just for the calculations. And so March 1st will be first month of the year, of each year actually. We call it Y, all right? Then April is going to be actually second month. Let me just say March actually, not March 1st. So this is the first month of the year, and this is going to be the second month again of the year Y. We add one more in here. May is going to be the third month. And December is going to be the 10th month. And January is going to be the 11th month. And February is the 12th month. However, for January and February, January is going to be considered as the 11th month of the previous year, Y minus 1. And February is going to be the 12th month this month, okay, of the year Y minus 1. All right? So we're always going to go back to actually the previous year. All right, for all other months except January and February, we're going to consider them from a previous year. All right. Also, we need to denote the days of the week. We're going to assign the numerical values for these. So out of convention, first we have to settle notations, and then we'll start doing the calculations. So, so these are the months. Now let's look at the days. So we're going to associate with Sunday is going to be 0. So the 0 day, basically. And then we have Monday will be 1, and so on. And Saturday will be the 6th day. All right? You associate with these. Now, we also have the following. We have 365, all right, which is the common year. All right, is congruent to 1 mod 7. And this is going to be a crucial congruence that we're going to be using, which means that, this is for common years, for any common year. Remember, common year is the 365 days. And we have 366 is congruent to 2 mod 7. All right, for any leap, including the century years, of course, that are leap years. All right, our derivation we're going to concentrate on. Okay, so this is our first goal. Is to find the day of the week of March fairs in a given year. This is say Y from the March fairs of the year or since the year 1600. Now, once we figure out a formula for calculating for March, then we're going to proceed to talk about other months, okay? So this is the first objective that we're going to first achieve, all right? So always we're going to do for March. All right. First of all, we had these formulas in here for the common year and so on. If we so if we denote, we're going to let D sub Y, all right, this stands represent the date of the week, so this represents the day of the week of March 1st of year Y. And where Y, of course, is bigger than 1600. Now, when we go, actually, we're going to express, all right, the dy in terms of the previous year, all right? Now, between March 1st, all right, of year Y minus 1 and year Y, actually they're provided if Y is a common year, and let me actually put N there. And if Y, the year that we are in, is a common year, then the dy is actually going to equal the dy minus 1 plus 1 mod 7. In other words, the day, a certain day is going to be advanced by 1 day. All right, so if March 1st in a certain year, all right, was on Monday, means it has the value 1, then the next year after that, where the next year is a common year, is going to be on Tuesday. So this is what this one is saying. Now, on the other hand, this is going from 1 year to the next year, okay? So this is not a cumulative, 1 year, the year before that, okay? So on the other hand, if Y, the year Y is leap year, is a leap year, then the formula is going to be dy is equal to dy minus 1 plus 2. And we're going to express all of these in terms of congruences, okay, mod 7. Not equal because we could actually pass the number 7 actually or 6, so we need to go back to 0 and so on. All right. Now, for example, again, to just to illustrate this, if we take D, so for example, if we have D 1600, all right, is March 1st in 1600, then March 1st in 1601 is going to be D 1601 is going to be D 1600, whatever date this plus 1, because this is just a common year. And same thing, March 1st in 1602 is going to be given. Actually, let me put this one is again congruent mod 7. All of these are mod 7. And here, we write actually, well, D 1602 is going to be D 1600, and we got this one, and we're going to add 2 this time. All right, 1 and 1. So this is mod 7. The next year after that is the same 1603, still it's a common year, and this is D 1603, and this is equivalent to D 1600 plus the 3 on 7. Then the year 1604, it's a leap year. This is leap year. And this time, the D 1604 is going to be D 1600 plus 5. So we have to jump by 2 in here, mod 7. So in other words, to find a formula from the 1600, basically, for a certain date, we need to find the number of common years and the number of leap years, okay, from the 1600 to the year that we are interested in finding the day of the week. And we're going to do this one, of course, in general. So we're going to do these calculations. All right. So in other words, we have to, if I want to accumulate, all right, between, so in here, as you see, we are adding from the 1600, we add 1 at a time, all right, and between this is the number of years, which are common years, but when we go to a leap year, we need to add, you know, an extra one, basically, all right. Well, so this is our next step, is to, so in general, if I want dy, you know, again, remember this is for March 1st, all right? It's going to be whatever the March 1st in 1600, all right, plus the number of common years, all right? And we may need to add also L, which is the number of leap years, because it depends on, you know, what day and in what year, all right? Again, mod 7. Because we're not going 1 year at a time here. We're going actually the y in here, where y is bigger than 1600. All right. So in other words, what we have to do, we need to find where we actually here, where also L is the number of leap years between 1600 exclusive. We're not going to include the 1600 to the year Y, inclusive, this one, okay, inclusive. We have to include the year if it happens to be a leap year. All right, so then our next objective is to find L. All right, so we need to count how many leap years are there. So first, the number of years, the total number of years, in the time period, or in the time period, or date period is better. Between 1600, this 10, and I'll include this one till Y, that are leap years. These are going to be the multiples of 4, okay? And remember, this number is given by, okay, so these are the leap years that are, these are that are divisible by 4. And remember, we could use the greatest integer function to do this, and this number is the total number y minus 1600 divided by 4. So this is the number among the numbers from 1601 to y that are divisible by 4 is given by the greatest integer of this. All right, and we could simplify this as y over 4 minus 1600 over 4, and since 1600 divides, so we come up with actually 400, sorry. And this is equal to, because 400 is an integer, so we could write it as y over 4 minus 400. The next thing we need to calculate is the number of centuries, okay? So number of century years again from between 1600 exclusive and year 1 inclusive. So this one is going to be those numbers that are multiples of 100, okay, or divisible by 100. And this number is y minus 1600 divided by 100. And this is again, we simplify this to y over 100 minus 60. Now, among these years, the century years, we need to find the leap years. Okay, and these are the ones which are multiples of 400 or divisible by 400. So among the century years, that are leap years, equivalent to say divisible by 400. And this number is given by this. Is again y minus 1600 divided by 400. And when I simplify this again, I get y over 400 minus 4. All right, then now we can see what's the total number of leap years. So the total number of leap years, so L, or number of leap years, or leap years, from 1600, again exclusive to year Y, is given by this. L is equal, we're going to start with, first of all, the this was actually the regular leap years, all right? Not century. Then we're going to subtract from these the century years, all right, which is y over 100 minus 60. And then we're going to add the leap years. So these are the century years. We have to take them out, all right, but this includes all the years. So we're going to take the century years, and then we're going to add the leap century years, which is y over 400 minus. But when we add up and simplify all of this, adding the negative 400 plus 16 minus 4, we end up with this formula for the leap years minus y over 100 plus y over 400, and the number turns out to be negative 388. All right, well, let's look at an example. Again, presenting a lot of formulas. Let's find how many leap years actually since 1600 to 1995. Okay, so let's calculate the number of leap years. So here's an example. We're going to find the number of leap years from 1600 to exclusive to 1995. course, 1995 is not a leap year, but so this is in general the way the formula works. All right, so the L in here is going to be y. We actually put the year itself, 1995, divided by 4, minus, again, 1995, divided by 100, plus 1995 divided by 400, and minus 380. And doing the brackets for each one of these fractions gives us the following values. The first one, it's 498. Then we have minus 19 plus 4 plus 388. All together give me 95 years. So there are 95 years from the 1600s to the 1995 that are actually leap years. All right. Now, we're going to develop an alternate formula for L, which is convenient to work with, okay? So we replace the year y by this. We're going to write y is equal 100 multiplied by c plus little y, where c is the century of year y, and y and little y is the year in that century, is the year in century S. Century C, sorry. Now remember the y in here, the little y is going to be bigger than or equal to 0 and less than 100. Because once y go to 100, then we'll go to the next set. Just to illustrate this convention here, or this notation, for example, 1982, we can write this one as 100 times 19, all right, plus 82. All right, so that's what it is. So this is the C, and this is little y. All right, now with this, then the formula for L takes the following form. All right, so with this notation for y, instead of using y, so therefore, L becomes equal to, remember what L is? So it's going to be 100 C plus Y. So this is the Y over 4 minus 100 C plus Y, again, over 100, then plus 100 C plus Y over 400, minus 388. And again, we're going to simplify all of this. We're going to divide by 4. We're going to come up with 25C plus Y over 4. Then this one we're going to have as just a C plus y over 100. And this one is going to give me C over 4 plus y over 400 minus 380. Well, so this one we can take the 25C out because it's an integral value. And this is y over 4. This one, again, we can take the C out. Now, y over 100, remember that y is less than 100. So which implies that y over 100 is actually less than 1. So the bracket of y over 100 is going to be equal to 0. So this is going to go to 0. And then this one, actually we could replace this one by, remember that we have the C. So let's look at this. C over 4 plus y over 400. Okay. So this is actually, this one is again less than 100. So if I replace it by the largest value, so this becomes C over 4 plus 100 over 400, which is equal to C over 4 plus 1/4. So when I take the bracket of this, C over 4 plus 1/4, this is going to be equal to C over 4. Okay, but we don't have enough to go to the next integral value for C over 4. So this means that we could replace this by just C over 4 and then minus 388. All right, I want to also simplify this a little more by adding all these numbers and so on. And this is equal, so 25, and C is actually is a century, so this is a whole number. So this gives me 24 C plus y, little y, sorry, over 4 plus C over 4 minus 388. And now, when we want to do this is mod 7, okay, so I want to make this is mod 7. But our calculation is going to be mod 7. I can replace the 24C by actually just the 3C. The brackets, they are not going to change. C over 4. And this is congruent to actually negative 3 mod 7. So this becomes minus 3. All right, so this is L. Now I want to go back to the March 1st of any year. So a formula for March 1st for any year. What day of the week it would be? Remember earlier we have this formula, dy is equal to d1600 plus y minus 1600, so the total number of years plus leap years, and this is actually congruent, we're going to say mod 7. Now we're going to replace the L by what it's equal to, all right, and also the Y, what it's equal to. So we're going to replace this and replace this, all right, and this is what we get. Right, so this is congruent to D1600, and the Y 100C plus little y minus 1600. And the L, the final form of the L is a 3C plus Y over 4 plus C over 4 minus a 3. And all of this is mod 7. All right. Again, when we simplify all of this, we can have it concisely written as, okay, using congruences again, D 1600 plus this one and this one. This could be 103 C, then plus Y minus the numbers, which is 1603, all right, and plus the brackets, Y over 4 plus C over 4, mod 7. One last simplification is to reduce these numbers all to mod 7. And it turns out that we could do this, replace this is by actually negative 2. So this one, 103 is congruent to negative 2 mod 7. So I want to take negative C in here. Then we have Y. Then we have this one. Actually is congruent to 0 mod 7. So this is congruent to 0 mod 7. And this one is congruent to negative 2 mod 7. So we're using these ideas, and then we have the plus Y over 4 plus C over 4 mod 7. All right, so this is March 1st. We know March 1st for any year now. So this is the relationship between March 1st, 1600, which we denote by D 1600, and March 1st, year D1. Sorry, this is the relationship between the day, all right? The day of, not just anything, that day of March this and the day of year 1. All right? Why? It could be anyone. So if we know one of them, then we know the other one. So this relationship actually goes both ways. So let's look at an example again to see how this calculation is done. We're getting almost there. Few more things. Need to take care of months, and then we'll be it. So here's an example. March 1st, 1982 was on Monday. We need to find March 1st, 1600. What day of the week this one is? So in here, what we are given here is D 1982. So this is our Y is equal to 1, okay, because Monday is 1. And to do the calculation in here, we need to write 1982. This is equal 100 times 19 plus 82. So C is equal to 19. Little y is equal to 82. And if you plug these numbers in here, So you get 1 on this side of the equation, and the D1600 that we are seeking, minus 2 times 19 is 38, plus 82, plus 82 over 4, plus 19 over 4, and we're going to reduce all of this mod 7. So when you do your calculation in here, of course, you want to solve this one for D1800, you will find that D1600 is equal, okay, so this is going to be mod 7, so it means March 1st, 1600 was on Wednesday. All right. Now, the next step is we're going to work on the months. Okay. So we need to determine the day of the beginning, the first of each month. Okay, so let me write this objective. And from there, we can then go from March to any other month and any other day. All right. So next objective. Next, we need to determine the day of the week on which the first of the month of each month, not just 1 month, each month of a given year fall. Now, to do this calculation again, we have 30 is congruent to 2 mod 7. So, in other words, if we have a 30-day month, all right, so this means this implies a 30-day month. Advances by 2 the weekday in which the next month begins. Which the next month begins. However, at 31 days, a 31-day month it increases by 3 days. Now with this, when we do the calculations, for example, okay, so for example, if I want to go for So if I go with June 1st, all right, then this will be greater than, let me actually have more space in here. I want to write a statement. This is the form I want to say. So for example, June 1st will be 3 plus 2 plus 3, and this is congruent to 1 mod 7 greater than March 1st of the preceding year. The previous year. The reason for this, because we have, from March itself is 31 days. So we add the 3. Then we have April, 30 days. And then we add 2. And then we have May, 31 days. And we add the 3. So from here, we actually advance by, because of the congruence, of course, by 1. But the total number is actually equal 8 days. All right? Now, for every month, starting from March, to consider it as a 0. So we have this table which gives us the by how much each month will advance from one year to another. So March have 0, and then we have April, actually 3, all right, because from March here we have 31 days. Then we have May, 5, another 2 days, June, 1, and we need to reduce mod 7, of course, in here, and then July, 3, August, 6, September, 2, October, 4, November, 0, December, 2, January, 5, and February, 1. Now, this is very hard to remember, okay? In 1882, a person of name Christian Zeller found a formula, found the following. Formula for month M was 0, 1 up to, actually from 1, starting from 1 up to 12. The expression that give actually these values. All right, this expression looks like people, think that it was done by trial and error, 2.6 m minus 0.2 minus 2 mod 7. And of course here, this is the bracket function, okay, so the greatest integer function, which you can try for getting some of these values, just plugging in the month, okay. So this is the first month, this is the second month, third, fourth, and so on, okay. So this is month 12. So this is what the M stands for in here. All right. Now, I have a couple more things in here, almost. To have the days now. We need the days of the week for any month, for any day. And to do this, so we have the number then number of the first day of the mth month of the year Y is given by, in terms of March, okay, dy. So this, remember, this is March 1st year Y. So it's gonna be, we're gonna add to this, okay? So the first day we're gonna add an appropriate number to it, which is 2.6m minus 0.2 minus 2 mod 7. All right, so now we figured out what dy is. Remember that the thing is. So we need to just add this equation to find the first of the month, okay, of any month, basically. Now, with this, we need to come up with the final result, okay? Put this together, which is you need to just substitute for the dy by what it is. So the final result here, finally, the number W of day D month M, year capital Y, which we can write as 100C plus little y, is given by this. W is equal D minus 1 plus just how many days to get to this day, and then the beginning of the month, which we have 2.6 m minus 0.2 minus 2 mod 7. I'm just going to add, the numbers to get to D, which is D minus 1, and add it to the beginning of the month, okay? Now, when I substitute again for this, dy, what it is equal to, we end up with the final formula here for the date, 2.6m minus 0.2, then minus 2c plus y over 4 plus c over 4 mod 7. All right, so this is what is the W, means the day of the week for a certain day. Then the author put this in a form of a theorem, okay, which I'll let you with the details, assumptions there, and so on. All right? I want to look at a couple of examples just to illustrate this idea of how this formula works. All right? And this will be it. So I want to look at, so I'll do the simple example. Look at May 11, 1953, and find the, so example 1. You need to find the day. Of the week of May 11, 1953. All right. So in this case, first of all, in the formula, D is equal 11. The M is the month of May, is, remember May is the 3rd month, all right? So let me see it here. May is, M is equal to 3, and 1953 is equal 100 times 19 plus 53. So this makes the C is equal 19. The Y is equal 53. And we are ready to plug in all the numbers. All right, so the W is going to be 11 plus 2.6 times 3 minus 0.2 minus 2 times, this is 38 plus 53 plus 53 over 4 plus 19 over 4 mod 7. And you plug all these numbers in, and these are the values you get. This is 11. The next number gives you actually 7 minus 38 plus 53. And this gives you 4. And 19 over 4 gives you actually, let's see it here. 19 over 4, this gives you 3 actually. All right. Mod 7. And this happens to be actually is equal to congruent to 50 and mod 7. And this congruent to 1 mod 7. So in other words, this date is actually Monday. All right. So this is occurred on a Monday. All right, let's do a calculation where we use a January, where we have to consider a previous year, okay? Let's look at an example of finding so this way you can now design your own calendars. You know what days of the week each month occur, and you know what the leap years and so on. So let's find the day of the week. They celebrated January 1st of January 1st, 1900. All right, so The month in here is going to be 11 of year 1899. All right, so we have to go to the year before. All right, and the D is equal 1. We know the M, and now we need the 1800. So this is 100 multiplied by 18 plus 99. So we have C is equal 18, and little y is equal 99. And now we can have this. So what's the W? It's going to be equal. It's going to be day 1 plus 2.6 multiplied by 11 minus 0.2 minus 2C, which is 18, plus Y, 99, then the 18 over 4 and 99 over 4 mod 7. When you do all these calculations, you find actually, again, this is congruent to 1 mod 7. So again, this date is on Monday. All right, so it looks like all the dates occur on Monday. Oh, no, that's not true. All right, we're going to stop right here. And hopefully, I will get started on chapter 7, where we're going to see some good stuff.